Good evening, and welcome to the library. Tonight, we'll drift into a question that has haunted human consciousness for centuries. We are going back through time to a frost-covered window in Bavaria, where a young mathematician sat beside a warming fire contemplating whether everything he had ever experienced might be nothing more than an elaborate deception. Not the modern computer simulations we imagine today, but the deeper philosophical foundations that rest just beneath our digital age assumptions. What we often imagine as a recent technological concern was actually born in the methodical doubt of René Descartes' Winter Meditations, where systematic skepticism, the careful architecture of uncertainty, and the discovery of one unshakable truth revealed a profound, calming realization about the nature of consciousness itself, that even in a world of total illusion, the very act of thinking proves something real exists. If these ancient questions bring you a sense of wonder about the continuity of human curiosity, please consider leaving a like or subscribing. It helps the channel grow and lets more people find a peaceful way to learn. Share what you think in the comments. Would you remain true, even if everything else were an illusion? Close your eyes and relax your mind. Let's begin our gentle descent into Chapter 1, which explores how a 17th-century philosopher's winter contemplations would eventually grow into our modern questions about simulated realities, and discover why the search for certainty in an uncertain world remains as relevant today as it was in that small, heated room 4 centuries ago. Chapter 1. Philosophical Origins of the Simulation Idea. The Winter of Systematic Doubt. In a small, stove-heated room in the Bavarian town of Neuburg an der Donau during the harsh winter of 1619, a 23-year-old mathematician and natural philosopher sat wrapped in contemplation, undertaking what would prove to be one of the most audacious intellectual ventures in human history. René Descartes, this methodical doubter who would reshape the very foundations of human thought, had withdrawn from the tumultuous world outside to pursue what he called his great rebuilding, a systematic examination of everything he had ever believed to be true. The world beyond his frost-covered window was a realm of unprecedented upheaval that stretched across the entire fabric of European civilization. Snow fell quietly over a continent convulsed by the 30 Years' War, where Catholic and Protestant armies had been locked in devastating conflict that would ultimately claim 8 million lives. Imperial forces under Ferdinand II pressed their advantage against Protestant coalitions, while Swedish interventions under Gustavus Adolphus transformed local religious disputes into a continental struggle for political supremacy. Cities like Magdeburg had been burned to the ground with such ferocity that contemporaries spoke of the Magdeburg Wedding, a massacre so complete that scarcely anyone survived to describe it. Populations fled before advancing armies that stripped the countryside bare, leaving behind a demographic catastrophe that would scar German-speaking lands for generations. This was an age when the very foundations of knowledge appeared to be shifting beneath the feet of thinking beings everywhere. The old certainties of medieval Christendom lay shattered not merely by military conquest, but by intellectual revolution. Galileo Galilei's revolutionary telescope had recently revealed 4 previously unknown moons circling Jupiter, suggesting that the heavens themselves might not conform to the ancient certainties inherited from Aristotle and Ptolemy. The Medicean stars, as Galileo had diplomatically named these satellites, challenged the fundamental assumption that all celestial bodies must orbit the Earth. Johannes Kepler had demonstrated that planetary orbits followed elliptical rather than circular paths, undermining the classical belief that heavenly motions must exemplify perfect geometric forms. The scientific revolution was simultaneously inspiring and terrifying in its implications. If human senses and inherited wisdom could be so thoroughly mistaken about the basic structure of the cosmos, what other fundamental beliefs might prove equally unfounded? The mechanical philosophy emerging from the work of figures like Galileo and Kepler suggested that the natural world operated according to mathematical laws rather than purposeful design, challenging traditional notions of divine providence and human significance. In his carefully heated chamber, warmed by the innovative stove heating system that had been recently introduced to Northern European architecture, Descartes surrounded himself with the tools of mathematical precision and philosophical rigor. The room contained his mathematical instruments, brass compass and rulers for geometric construction, an astrolabe for astronomical observation, tables of logarithms that simplified complex calculations. Volumes of classical and contemporary philosophy lined makeshift shelves, works by Aristotle and Aquinas representing the scholastic tradition he was beginning to question, alongside newer treatises by Galileo and Kepler that suggested radically different approaches to understanding natural phenomena. Most significantly, the room contained the manuscripts on which he would record insights that would echo through nearly 4 centuries of subsequent inquiry. By candlelight that flickered across pages covered with his precise Latin script, this architect of systematic skepticism was crafting questions that would reach their most startling contemporary expression in our current debates about simulated realities and computerized universes. His notebooks from this period reveal a mind grappling not merely with specific philosophical problems, but with the fundamental question of method itself. How should a rational being proceed in the search for reliable knowledge? The intellectual atmosphere of early 17th-century Europe provided both inspiration and urgency for Descartes' methodical investigations. The printing press had democratized access to competing philosophical and scientific traditions, creating what we might now recognize as an information overload problem. Ancient texts, newly translated from Greek and Arabic, presented worldviews that contradicted both each other and Christian doctrine. Jesuit missionaries returning from China described sophisticated philosophical traditions entirely independent of European development. The diversity of human opinion about fundamental questions had become impossible to ignore. Descartes had received a thorough education at the Jesuit College of La Flèche, where he had mastered the scholastic curriculum that represented the culmination of medieval learning. He had studied Aristotelian physics, Ptolemaic astronomy, and Thomistic theology, intellectual frameworks that had served European civilization for centuries. Yet his mathematical training had also exposed him to the power of geometric demonstration, where conclusions followed with logical necessity from clearly stated premises. The contrast was stark. While philosophical and theological authorities disagreed about fundamental questions, mathematical proofs commanded universal assent among competent practitioners. But on that winter day, as he sat wrapped in contemplation beside his warming stove, the father of modern philosophy was not thinking about computers or virtual worlds, technologies that lay centuries in the unimaginable future. Instead, this careful analyst of human knowledge was wrestling with a more fundamental question that had haunted philosophers since antiquity. How can finite minds like ours distinguish between genuine knowledge and the mere appearance of knowledge? How can we tell the difference between reality as it truly is and the most convincing possible illusion? The question was not merely academic. The religious wars devastating Europe had demonstrated how deeply held convictions could lead to catastrophic practical consequences when they proved mistaken. The scientific revolution was revealing that common sense and traditional authority could be systematically wrong about the basic structure of reality. In such circumstances, the search for reliable knowledge was not intellectual luxury but practical necessity. Descartes' response to this epistemic crisis drew inspiration from mathematical practice. but extended far beyond technical mathematical questions. Just as mathematicians began geometric proofs by establishing certain axioms and then deriving conclusions through valid inference, Descartes proposed to begin philosophical inquiry by identifying beliefs that could withstand the most systematic possible doubt. Only such indubitable foundations could support a reconstruction of human knowledge adequate to the challenges of a rapidly changing world. The methodological innovation was revolutionary in its scope and ambition. Previous skeptics had typically employed doubt to demonstrate the impossibility of knowledge, concluding that wise people should suspend judgment about fundamental questions. Descartes transformed doubt from a destructive weapon into a constructive tool, using it to clear away unreliable beliefs and reveal the solid foundations on which genuine knowledge could be built. What emerged from his extended winter meditations was a solution so radical, so unsettling in its implications, that it continues to disturb and fascinate philosophers today. In the quiet of his Bavarian retreat, removed from the chaos of religious warfare and intellectual controversy, Descartes conceived what he called an evil demon, a being of immense power and cunning that had dedicated itself entirely to deceiving him about the nature of reality itself. The genius of this thought experiment lay not merely in its imaginative boldness, but in its systematic character. Descartes was not simply proposing another skeptical scenario to add to the catalogue of philosophical puzzles. He was constructing a methodical test that could distinguish between beliefs that merely seemed certain and those that were genuinely indubitable. The evil demon represented the ultimate skeptical challenge, precisely because it systematized and intensified every possible source of error that had been identified in previous philosophical traditions. The cultural resonance of Descartes' scenario extended far beyond professional philosophical circles. The idea of systematic deception by powerful supernatural forces spoke to widespread anxieties about religious and political authority that had been intensified by the ongoing wars of religion. If earthly authorities could be so thoroughly mistaken about fundamental questions, and if human senses could deceive us about the basic structure of the cosmos, then perhaps the most radical skeptical possibilities deserve serious consideration. The demon's absolute deception. This malevolent intelligence that emerged from Descartes' systematic analysis possessed what the revolutionary thinker described as utmost power and cunning. The evil demon was not merely mischievous or occasionally deceptive. It represented the ultimate skeptical challenge, a being that employed all his energies to ensure that every experience, every sensation, every apparent memory formed part of an elaborate and systematic fiction. In conceiving this possibility, the man who would revolutionize human self-understanding had unknowingly laid the conceptual groundwork for what we now call the simulation hypothesis. The psychological sophistication required for such comprehensive deception was staggering in its implications. Consider the demon's intellectual challenge: to create and maintain a coherent alternative reality that would satisfy the scrutiny of a systematic doubter like Descartes himself. This supernatural intelligence would need to understand not merely how to create individual false sensations, but how to weave them together into a convincing narrative of experience that would withstand the most careful analysis. The demon's deceptive project would require what we might recognize as a form of cosmic dramaturgy. Every apparent interaction with the external world would need to be scripted with perfect consistency. If the demon made it seem that Descartes was writing with a quill pen, the texture of the parchment, the resistance of the ink, the slight scratching sound of the nib across the surface, all of these sensory details would need to coordinate perfectly to maintain the illusion. More challenging still, The demon would need to ensure that when Descartes returned to examine his writing later, the words would appear exactly as he remembered writing them, creating a false sense of temporal continuity. The theological implications of Descartes' evil demon scenario were as profound as they were troubling. In medieval Christian thought, deception was fundamentally associated with Satan, the father of lies who had corrupted human understanding through the original temptation in Eden. Yet Descartes' demon-possessed capabilities that seemed to exceed even traditional conceptions of diabolic power. Where Satan was typically understood to work through the corruption of human nature and the exploitation of existing weaknesses, the evil demon operated through the wholesale fabrication of alternative reality. This raised disturbing questions about the relationship between divine omnipotence and the possibility of systematic deception. If God was truly omnipotent, could he create experiences indistinguishable from reality but lacking any foundation in actual truth? The question was not merely academic for 17th-century thinkers who understood divine power in terms of absolute sovereignty over every aspect of creation. Descartes himself would later argue that God's perfect goodness prevented him from engaging in systematic deception, but the logical possibility remained unsettling. The demon that haunted Descartes' philosophical imagination possessed capabilities that sound remarkably similar to those attributed to the supercomputers of contemporary science fiction. This supernatural intelligence could generate convincing sensory experiences that bore no necessary relationship to any external reality. It could make it seem to the winter philosopher that he possessed hands when he had none, that he was sitting by a warming fire when no fire existed, that the external world contained solid objects when nothing beyond the demon and the deceived mind actually existed in the ultimate scheme of reality. The phenomenology of total deception, what it would actually feel like to be comprehensively deceived about reality, presented conceptual challenges that pushed against the limits of human imagination. The victim of such deception would presumably experience all the normal varieties of human emotion: joy and sorrow, hope and fear, love and hatred. Yet none of these emotions would have appropriate objects in reality. The demon's victim might feel grief for deceased loved ones who had never existed, take pride in achievements that were entirely fictitious, or experience romantic love for beings who are nothing more than sophisticated illusions. Most unsettling of all, this methodical deceiver could implant false memories with perfect precision, making it seem as though Descartes had always lived in a world populated by material objects and other thinking beings, when such a world had never existed. The demon could create the illusion of personal history, making the present moment seem connected to a rich autobiographical narrative that was entirely fabricated. It could simulate the experience of learning, discovery, and intellectual development, while ensuring that no genuine knowledge was ever acquired. The memory manipulation required for such comprehensive deception would need to be extraordinarily sophisticated. The demon would need to ensure that each false memory connected appropriately with others, creating a coherent life story that could withstand introspective examination. When Descartes remembered his education at La Flèche, for instance, the demon would need to provide not just the major facts but all the supporting details. The specific teachers who had instructed him, the layout of the college buildings, the daily routines of student life, the emotional textures of particular experiences. The epistemic implications of perfect deception scenarios pushed beyond traditional skeptical challenges toward more fundamental questions about the nature of experience itself. If the demon could simulate not just sensory experiences, but also the inner life of reflection, emotion, and memory, what would distinguish genuine consciousness from its perfect simulation? The demon's victim would presumably experience themselves as a thinking, feeling being with a rich inner life, but this entire phenomenology would be artificially generated. The technological sophistication implied by the demon's capabilities anticipated developments that would not become conceivable for centuries. The demon would need something analogous to what computer scientists now call real-time rendering, the ability to generate complex sensory experiences instantaneously in response to the victim's mental state and apparent actions. If Descartes decided to look more closely at his hand, the demon would need to provide enhanced visual detail immediately. If he chose to touch his face, the demon would need to coordinate tactile sensations with proprioceptive feedback about the movement of his arm. The computational requirements for such real-time simulation would be staggering even by contemporary standards. The demon would need to track not just Descartes' conscious thoughts and decisions, but also the myriad unconscious processes that shape human experience. The automatic adjustment of breathing to physical activity, the subtle changes in heart rate that accompany emotional states, the complex feedback loops between expectation and perception that shape sensory experience. When Descartes wrote about experiences being artificially induced by a powerful external intelligence, he was unknowingly describing the basic architecture of virtual reality systems that would not be technologically feasible for centuries. When he worried about the reliability of sensory experience in the face of possible systematic deception, he was raising questions that computer scientists and philosophers of mind continue to grapple with in our age of increasingly sophisticated digital simulations. The demon's apparent omniscience raised further conceptual puzzles. To maintain perfect deception, the demon would need to understand not just how reality appears to human consciousness, but how it actually is. The demon could not simulate the experience of perceiving a tree without understanding what trees are actually like, could not fake the sensation of warmth without comprehending the nature of temperature, could not create the illusion of mathematical reasoning without grasping mathematical truth. This suggested a paradoxical relationship between deception and knowledge. The perfect deceiver would need to be perfectly informed about reality in order to create convincing alternatives to it. The demon's comprehensive falsehood would require comprehensive truth as its foundation. This philosophical irony would later inspire critics who argued that systematic deception was self-undermining, that the very possibility of creating perfect illusions presupposed access to perfect truth. The motivational question, why would such a being dedicate itself to comprehensive deception, received little explicit attention from Descartes but opened rich territories for philosophical speculation. Unlike human deceivers who typically seek some advantage through their dishonesty, the evil demon appeared to engage in deception for its own sake. This suggested a form of malevolence, so pure that it sought the corruption of knowledge and truth as ultimate ends, rather than as means to other goals. The demon's relationship to time presented additional conceptual challenges. Perfect deception would require not just synchronic consistency, ensuring that all aspects of experience at any given moment fit together coherently, but also diachronic consistency, ensuring that experiences across time created convincing patterns of cause and effect, learning and development, continuity, and change. The demon would need to be simultaneously present at every moment of the victim's experience while maintaining a kind of eternal perspective that could coordinate the entire temporal narrative. The scope of the demon's deceptive project raised questions about whether such comprehensive falsehood was even logically possible. Could a being create experiences that were systematically false about everything, while remaining coherent and consistent? Critics would later argue that total deception was self-contradictory, that some aspects of experience must be veridical for deception to be possible at all. Yet the logical challenges only highlighted the philosophical significance of Descartes' thought experiment. In conceiving the evil demon, the methodical doubter had created a scenario that pushed skeptical reasoning to its absolute limits. Whether or not such comprehensive deception was metaphysically possible, the mere conceivability of the scenario revealed something important about the structure of human knowledge and the relationship between consciousness and reality. The methodical architecture of doubt. What made Descartes' insight so revolutionary was not merely its imaginative boldness, but the methodical rigor with which this systematic doubter pursued its implications. This was not idle speculation or intellectual play, but what he termed methodological doubt, a systematic process of subjecting every belief to the most stringent possible scrutiny. Like a master architect who carefully dismantles a building to examine the soundness of its foundations before constructing something new and more stable, Descartes sought to identify which of his beliefs, if any, could withstand even the most hyperbolic doubt. The architectural metaphor that shaped Descartes' philosophical method drew on his mathematical training and his experience with practical construction projects. During his time in Bavaria, he had observed the rebuilding of structures damaged by the ongoing warfare. He noticed how builders who attempted to repair buildings on unstable foundations often saw their work collapse again, while those who took the time to excavate down to bedrock could construct edifices that would endure for centuries. The lesson seemed clear. Lasting intellectual construction required foundations that could bear the full weight of systematic investigation. The methodological character of Cartesian doubt was crucial to its philosophical significance. Unlike skeptics who question the possibility of knowledge in order to establish skepticism as a permanent philosophical position, Descartes employed doubt as a tool for discovering certainty. His goal was constructive rather than destructive, to find beliefs so clearly true that they could serve as foundations for rebuilding human knowledge on more secure foundations. This represented a fundamental departure from the skeptical traditions that had emerged from ancient Greek philosophy. Academic skeptics like Arcesilaus had argued that the wise person should suspend judgment about all non-evident matters, living according to probability rather than certainty. Pyrrhonian skeptics like Sextus Empiricus had employed doubt to achieve ataraxia, a state of tranquil suspension of judgment that freed the soul from the anxiety of seeking absolute truth. Both traditions treated doubt as an end in itself rather than as a means to knowledge. Descartes' innovation was to transform doubt from a terminus into a method. Rather than seeking the peace of suspended judgment, the methodical doubter sought the security of indubitable knowledge. This required pushing doubt to its absolute limits in order to discover what, if anything, could survive the most comprehensive possible scrutiny. The process of methodological doubt proceeded through several carefully orchestrated stages, each designed to eliminate different classes of potentially unreliable beliefs. The systematic character of this progression reflected Descartes' mathematical training, where complex proofs were constructed through sequences of simple steps, each following necessarily from what had been established previously. The challenge of sensory deception. Descartes began with the most obvious sources of error, sensory experiences that had sometimes proved deceptive. The examples he chose were drawn from common experience and designed to be immediately recognizable to any reflective person. The stick that appears bent when partially submerged in water provides a paradigmatic case of sensory deception. What seems to be a simple perceptual fact, the stick's apparent curvature, proves false when the stick is removed from the water and appears straight again. The phenomenon of perspective illusion offered another compelling example. A distant tower appears round to the naked eye, but reveals its square structure when approached more closely. This type of deception suggests that spatial distance can systematically mislead perception, making objects appear to have properties they do not actually possess. The implications extend far beyond individual cases. If our senses can be wrong about basic geometric properties like shape, what confidence can we have in sensory testimony about the nature of external objects? Phantom limb sensations provided an even more unsettling example of sensory unreliability. Veterans who had lost limbs in the ongoing European conflicts reported continuing to feel pain, itching, or movement in their amputated extremities. These vivid sensations seem to provide clear evidence of the existence and condition of body parts that medical examination proved to be entirely absent. If the body could generate such convincing false sensations about its own state, what guarantee could there be that any sensory experience corresponded to reality? The variety of sensory deceptions catalogued by Descartes and his contemporaries seemed to follow certain patterns. Sensory systems appeared most reliable when operating under optimal conditions: clear light for vision, moderate temperatures for touch, quiet environments for hearing, but became increasingly unreliable as conditions departed from these norms. Yet even under apparently optimal conditions, careful investigation sometimes revealed that sensory appearances were misleading. The psychological analysis of sensory deception revealed the complex ways in which expectation, attention, and interpretation shaped perception. The same visual stimulus could be perceived as a goblet or as two faces in profile, depending on how attention was directed. Auditory experiences could be shaped by expectation, hearing one's name called in the sound of wind or water when anxiously awaiting a message. These phenomena suggested that perception involved active construction rather than passive reception, raising questions about whether any sensory experience could be taken as simply given. The dream argument's deeper challenge. The dream argument constituted the next stage of methodological doubt, addressing beliefs that seemed immune to the standard cases of sensory deception. Even if particular sensory experiences could be misleading, surely the general categories of sensory experience, color, shape, size, motion, provided reliable access to the nature of reality. Descartes' analysis of dreams revealed that even this more general confidence might be misplaced. The phenomenology of dreaming presented a profound challenge to the reliability of conscious experience. In dreams, people regularly have experiences that feel completely real, but correspond to nothing in waking reality. The dreaming mind seems to see, hear, touch, and move through environments that exist only in sleep. More disturbing still, the dreaming person typically takes their experiences to be real while dreaming, only recognizing their illusory character upon waking. Descartes developed several specific examples to illustrate the dream argument's force. A person might dream of sitting by a fire, feeling its warmth and seeing its light, while actually lying asleep in bed. The sensory experiences of warmth and light would be vivid and convincing during the dream, indistinguishable from waking experiences of the same type. Only upon waking would the person recognize that no fire had actually been present. The temporal structure of dream experiences provided additional grounds for doubt. Dreams often involve complex narratives that seem to unfold over extended periods, yet sleep research suggests that even lengthy dream narratives typically occur during brief periods of REM sleep. This temporal compression implies that the dreaming mind can generate the subjective experience of duration that bears no necessary relationship to objective time. The logical structure of the dream argument was more subtle than initial appearances suggested. Descartes was not simply observing that dreams sometimes contain false beliefs, but rather arguing that dream experiences were indistinguishable from waking experiences while they occurred. If experiences that felt completely real could be entirely illusory, how could anyone be certain that their present experiences were not similarly illusory? The argument's force extended beyond particular sensory experiences to challenge confidence in the general framework within which experience occurs. Even if a person could not be certain whether they were seeing an actual fire or dreaming of a fire, surely they could be confident about the general categories that structured such experiences: space, time, shape, number. Yet careful analysis of dream experiences suggested that even these fundamental categories might not be reliable. Dreams regularly involve impossible geometries where spaces are simultaneously large and small, or temporal sequences where effect precedes cause. The dreaming mind accepts these impossibilities as natural features of dream reality, suggesting that even the most basic logical and mathematical principles might not govern conscious experience as reliably as normally assumed. Mathematical truths under siege. The final stage of methodological doubt targeted what seemed to be the most certain knowledge available to human beings: mathematical and logical truths. Even if sensory experience was unreliable, and even if the distinction between dreaming and waking was problematic, surely mathematical demonstrations like 2 plus 3 equals 5, or the square has 4 sides, remained indubitably true. Descartes' analysis of mathematical knowledge revealed subtle ways in which even apparently certain truths might be subject to doubt. Mathematical reasoning required not just the apprehension of abstract relationships but also the capacity for extended chains of inference. Complex mathematical proofs involve dozens or hundreds of individual steps, each depending on the accuracy of memory in preserving previous results. If memory could be systematically unreliable, then even mathematical knowledge might be undermined. The possibility of systematic cognitive error provided another avenue for doubting mathematical truths. Perhaps human minds were systematically prone to certain types of logical mistakes that made false propositions seem obviously true. The history of mathematics revealed numerous cases where propositions that had seemed obviously true were later discovered to be false. If mathematicians could be wrong about complex proofs, perhaps they could be wrong about simple ones as well. The evil demon hypothesis pushed these concerns to their logical extreme. A sufficiently powerful deceiver could ensure that mathematical reasoning systematically generated false conclusions, while feeling completely convincing to the reasoning subject. The demon could make it seem that 2 plus 3 equals 5, when the correct answer was actually something entirely different. It could implant false logical intuitions that made invalid arguments appear valid, and valid arguments appear invalid. This final stage of doubt was perhaps the most unsettling because it challenged not merely the content of knowledge, but the very capacity for rational thought itself. If mathematical and logical reasoning could be comprehensively unreliable, then the tools required for evaluating evidence and constructing arguments might themselves be fundamentally corrupted. The methodical doubter would be left without any reliable method for distinguishing truth from falsehood. The pedagogical structure of doubt. The progression through these stages of doubt was carefully designed to lead readers through an increasingly radical process of philosophical reflection. Each stage built on the previous one while introducing new levels of skeptical challenge. The movement from sensory doubt to dream doubt to mathematical doubt represented not merely an escalation of skeptical scenarios, but a systematic investigation of different types of knowledge and different criteria for certainty. The pedagogical effectiveness of this progression lay in its gradual character. Readers who might resist the immediate introduction of radical skeptical scenarios could be led step by step to appreciate the force of more extreme doubts. By beginning with familiar examples of sensory deception, Descartes established a framework for thinking about reliability and evidence that could then be extended to more fundamental questions. The psychological realism of Descartes' examples also contributed to their philosophical effectiveness. Rather than relying on abstract logical possibilities, he drew on experiences that were recognizable to any reflective person. Everyone had experienced sensory deceptions. Everyone had vivid dreams. Everyone had made mathematical errors. The universality of these experiences made the skeptical arguments feel personally relevant rather than merely academic. The cumulative effect of working through these stages of doubt was to create what Descartes called hyperbolic or metaphysical doubt, a form of skepticism so comprehensive that it called into question not merely particular beliefs, but the entire framework within which knowledge claims were ordinarily evaluated. This hyperbolic doubt prepared the ground for the discovery of indubitable knowledge by ensuring that anything that survived such comprehensive scrutiny would be genuinely certain rather than merely apparently so. The cogito's unshakable foundation. Yet Descartes' goals in proposing this radical scenario were ultimately constructive rather than destructive. Through the systematic application of methodological doubt, this careful analyst of human knowledge discovered that the demon could deceive him about the external world, about his body, even about mathematical truths. But could the demon deceive him about the fact that he was thinking? Here, in the depths of systematic doubt, Descartes discovered his famous bedrock, cogito ergo sum, I think, therefore I am. Even if everything else was illusion, even if the most comprehensive deception was taking place, the very fact of experiencing illusion proved the existence of something that could be deceived. The thinking subject, whatever its ultimate nature, could not coherently doubt its own existence without simultaneously confirming that existence through the very act of doubting. The logical architecture of the cogito argument possessed an elegant simplicity that masked profound philosophical complexity. The argument's basic structure could be formulated in multiple ways, each highlighting different aspects of its logical foundation. In its most straightforward interpretation, the cogito functioned as an inference. I think, therefore I am, suggested that existence followed necessarily from the fact of thinking. Yet, Descartes himself sometimes presented the insight differently, describing it not as an inference, but as an immediate intuition of the connection between thought and existence. The distinction between inferential and intuitive interpretations of the cogito generated extensive philosophical debate. If the cogito functioned as an inference, it seemed to require a suppressed major premise. Everything that thinks exists. But this universal principle would itself require justification, potentially undermining the cogito's status as an indubitable foundation. If the existence of thinking beings needed to be established before the cogito could function as a valid argument, then the cogito would be circular rather than foundational. The intuitive interpretation avoided this circularity by treating the cogito as a direct insight rather than a formal inference. On this reading, the thinking subject did not deduce its existence from general principles, but rather recognized immediately that thinking and existing were inseparably connected in its own case. The cogito revealed not a logical relationship between universal concepts, but an existential truth about the nature of conscious experience itself. The phenomenological analysis of the cogito revealed additional layers of philosophical significance. What exactly did Descartes mean by thinking in this foundational context? The Latin term cogitare encompassed a broader range of mental activities than the English thinking typically suggests. Cartesian thought included not merely abstract reasoning, but all forms of conscious experience: perceiving, imagining, feeling, willing, doubting, affirming, denying. The cogito established the existence not merely of a reasoning subject, but of a comprehensive conscious being. This expansive understanding of thinking had important implications for the scope of the cogito certainty. Even if the evil demon could systematically deceive the thinking subject about the content of its thoughts, the demon could not eliminate the fact that thinking was occurring. Whether a person was genuinely perceiving a tree or merely hallucinating one, whether they were correctly solving a mathematical problem or making systematic errors, whether they were remembering actual events or recalling implanted false memories, in every case, some form of conscious mental activity was taking place. The cogito thus established not merely the bare existence of something, but the existence of something essentially characterized by consciousness. This was not the thin existence of a mere logical subject, but the rich existence of a being capable of the full range of conscious experience. The thinking subject whose existence was guaranteed by the cogito was a being that could doubt, believe, hope, fear, love, hate, even if all the objects of these mental states were illusory. The relationship between the cogito and personal identity presented further philosophical challenges. Did the cogito establish the existence of René Descartes as a particular individual with a specific history and set of characteristics? Or did it establish only the existence of some thinking subject whose identity remained to be determined? The methodical doubt that preceded the cogito had called into question all beliefs about the thinking subject's specific characteristics, including its name, history, body, and relationships. The cogito seemed to establish what philosophers would later call numerical identity, the existence of one thinking subject rather than many, without determining any of the qualitative characteristics that would make this subject the particular person that others would recognize as René Descartes. The thinking subject revealed by the cogito was in some sense stripped of all determinate content, existing as pure consciousness without specific attributes or qualities. This raised profound questions about the relationship between consciousness and personal identity. If systematic doubt could eliminate belief in all the particular characteristics that seemingly made someone who they were, what constituted the core of personal identity? Was there some essential self that persisted through all possible changes in belief and experience? Or was personal identity itself a construction that could be dissolved by sufficiently radical skeptical challenge? The temporal structure of the cogito presented additional puzzles. The argument seemed to establish the existence of the thinking subject only in the present moment of thinking. When Descartes affirmed, "I think, therefore I am," he could be certain of his existence only for as long as the thought lasted. The moment the thought ended, the certainty ended with it. This suggested that the cogito provided not a permanent foundation for knowledge, but only a momentary glimpse of indubitable truth. Some interpreters argued that this temporal limitation undermined the cogito's foundational status. How could momentary certainty provide a stable basis for reconstructing human knowledge? Others contended that the limitation was less serious than it initially appeared. Although each individual instance of the cogito provided only momentary certainty, the insight could be renewed indefinitely. Every time the thinking subject reflected on its own existence, it could achieve the same immediate certainty that characterized the original discovery. The metaphysical implications of the cogito extended far beyond epistemological questions about knowledge and certainty. In establishing the indubitable existence of a thinking subject, Descartes had identified what seemed to be a fundamental feature of reality itself. The cogito suggested that consciousness, rather than matter or energy, might constitute the most basic level of existence, at least from the perspective of any being capable of philosophical reflection. This primacy of consciousness over matter represented a dramatic reversal of ordinary assumptions about the relationship between mind and world. Common sense suggested that material objects existed independently of consciousness, and that consciousness emerged as a sophisticated product of material processes. The cogito implied that consciousness was more fundamental than matter, at least in the order of knowledge, if not in the order of being. The cogito's implications for the nature of the self were equally radical. The thinking subject, whose existence was established by the cogito, seemed to be essentially immaterial. Systematic doubt had eliminated belief in the existence of the body and the material world generally, but it could not eliminate belief in the existence of the thinking subject. This suggested that the self was not essentially embodied, but consisted entirely in its capacity for conscious thought. The relationship between the cogito and the evil demon scenario revealed a deeper philosophical point about the limits of skeptical doubt. The evil demon could create comprehensive deception about the nature of reality, but it could not create deception about the existence of something capable of being deceived. This suggested that there were logical limits to the coherence of skeptical scenarios, that total skepticism was self-undermining because it presupposed the existence of a subject capable of entertaining skeptical doubts. The discovery of the cogito thus marked not merely the end of methodological doubt, but the beginning of a new phase of philosophical construction. Having identified one indubitable truth, Descartes could begin the process of using that truth as a foundation for rebuilding human knowledge on more secure grounds. The thinking subject, whose existence was guaranteed by the cogito, became the starting point for arguments establishing the existence of God, the reliability of clear and distinct ideas, and ultimately the existence of the external material world. Yet the cogito's foundational status also created new philosophical problems. If all knowledge had to be built on the foundation of the thinking subject's self-awareness, how could that subject achieve knowledge of anything beyond itself? The cogito seemed to establish the existence of consciousness but leave everything else in doubt. This threatened to create a philosophical prison in which the thinking subject could be certain only of its own mental states, while remaining forever uncertain about the reality of anything external to consciousness. The ripples of revolutionary doubt. The ripples from Descartes' winter meditations spread rapidly through European intellectual culture, transforming the landscape of philosophical inquiry in ways that continue to influence thought centuries later. By the end of the 17th century, philosophers across the continent were grappling with the implications of systematic doubt and the problems it revealed about the nature of knowledge, reality, and consciousness. Some philosophers, like Nicolas Malebranche, propose that we never directly perceive external objects but only ideas in our minds, making us dependent on divine guarantee for any knowledge of the external world. Others, like Pierre Bayle, pushed skeptical arguments even further than Descartes had, questioning whether reason itself could provide reliable guidance about ultimate reality. The questions raised by Cartesian doubt had opened fissures in the foundations of philosophical thought that could not be easily repaired. But it was in the British Isles that Cartesian doubt would undergo its most creative and paradoxical development, setting the stage for philosophical revolutions that would echo through the centuries and eventually find their most startling contemporary expression in our current debates about computational simulation and digital reality. Transitional centuries, the evolution of skeptical thought. The 18th and 19th centuries witnessed a remarkable series of philosophical developments that transformed the skeptical themes introduced by Descartes into increasingly sophisticated investigations of the relationship between mind and reality. Each generation of thinkers brought new conceptual resources to bear on the fundamental questions about knowledge and existence, creating an intellectual trajectory that would culminate in the technological scenarios of our own era. Hume's radical empiricism and the dissolution of certainty. David Hume, writing in Edinburgh during the mid-18th century, pushed the empiricist program inherited from Locke and Berkeley to conclusions so radical that they threatened to dissolve not merely particular knowledge claims but the very possibility of rational inquiry itself. Where Descartes had sought to rebuild knowledge on indubitable foundations, Hume's careful analysis suggested that no such foundations existed. Hume's investigation of causation proved particularly devastating to traditional confidence in rational knowledge. When we observe one billiard ball striking another, and see the second ball begin to move, we naturally assume that the first ball caused the motion of the second. Yet Hume's meticulous analysis revealed that experience provides access only to the succession of events, never to the causal connection itself. We see one event followed by another, but we never perceive the mysterious power or necessity that supposedly connects cause and effect. The implications of this analysis extended far beyond billiard balls to undermine confidence in scientific reasoning generally. All scientific knowledge seemed to depend on assumptions about causal relationships that could not be empirically justified. When Isaac Newton described gravitational attraction between masses, he was describing regular patterns of behavior, but he could not demonstrate that these patterns reflected genuine causal powers, rather than mere correlations that might cease to hold at any moment. Hume's analysis of induction revealed an even more fundamental problem. Scientific reasoning depended on the assumption that patterns observed in the past would continue to hold in the future. Yet this assumption could not itself be justified through experience, since experience was always limited to what had already occurred. The principle that the future will resemble the past could not be established empirically, without circular reasoning that assumed the very principle it sought to prove. The problem of personal identity presented another challenge to rational confidence. Hume's introspective analysis suggested that the self was nothing more than a quote, or collection of different perceptions, which succeed each other with an inconceivable rapidity, and are in a perpetual flux and movement. There was no underlying substance that persisted through time to constitute personal identity, only a stream of successive mental states connected by psychological associations. This dissolution of the self had profound implications for the skeptical scenarios that had emerged from Cartesian doubt. If there was no substantial self to be deceived, then the problem of distinguishing between genuine and illusory experience became even more complex. The very subject of possible deception seemed to dissolve under careful philosophical analysis. Hume's skepticism was more thoroughgoing than Descartes' methodological doubt because it questioned not merely the content of beliefs, but the rational processes through which beliefs were formed and justified. Where Descartes had used doubt as a tool for discovering certainty, Hume's analysis suggested that doubt was the natural terminus of careful philosophical reflection. Yet Hume himself recognized that such radical skepticism was psychologically unsustainable. Despite his philosophical arguments, he continued to believe in causation, induction, and personal identity in his everyday life. This led him to distinguish between philosophical reason, which dissolved these beliefs, and natural belief, which sustained them despite rational criticism. Human beings were constitutional believers, whose psychological nature prevented them from taking skeptical arguments to their logical conclusion. Kant's critical revolution and the conditions of experience. Immanuel Kant, writing in Königsberg during the late 18th century, responded to Hume's skeptical challenge by proposing what he called a Copernican revolution in philosophy. Rather than assuming that knowledge must conform to reality, Kant suggested that reality as we experience it must conform to the conditions that make knowledge possible. Kant's insight was that Hume's skepticism arose from assuming that the mind was passive in its relationship to experience. If the mind simply received impressions from external sources, then there would indeed be no way to establish necessary connections between different aspects of experience. But if the mind actively structured experience according to its own inherent principles, then some features of experience could be known with certainty, because they reflected the mind's own contribution to the constitution of experience. The transcendental argument that emerged from Kant's analysis had profound implications for skeptical scenarios. Systematic doubt was possible only within a framework that already presupposed the validity of certain fundamental concepts and principles. The very possibility of coherent experience required what Kant called categories of understanding. Concepts like causation, substance, and unity that organized sensory input into intelligible patterns. Kant's distinction between phenomena and noumena provided a new framework for thinking about the relationship between appearance and reality. The world as we experience it, the phenomenal world, was shaped by the mind's own contribution to the constitution of experience. But this left open the question of what reality might be like independently of human experience. The noumenal world. This distinction had complex implications for simulation scenarios. If experience was always already structured by the mind's own principles, then the difference between real and simulated experience might be less significant than traditionally assumed. Both genuine perception and systematic deception would need to conform to the same transcendental conditions that made experience possible. Kant's analysis of time and space as forms of intuition rather than features of reality in itself suggested that even the most basic aspects of experience might not correspond to the ultimate nature of reality. Time and space were not discovered in experience but were preconditions that made temporal and spatial experience possible. This implied that reality in itself might be neither temporal nor spatial, a conclusion that anticipated some features of contemporary physics. The critical philosophy thus provided resources for thinking about skeptical scenarios that went beyond both dogmatic realism and radical skepticism. Experience had a structure that could be known with certainty, but this structure reflected the mind's contribution to the constitution of experience rather than the ultimate nature of reality itself. German idealism and the mentalization of reality. The generation of German philosophers who followed Kant pushed his insights in directions that would have surprised the careful Königsberg professor. Johann Gottlieb Fichte, Friedrich Schelling, and Georg Wilhelm Friedrich Hegel developed philosophical systems that made consciousness or spirit the fundamental principle of reality itself. Fichte's Wissenschaftslehre proposed that all reality emerged from the activity of an absolute ego that posited both itself and its opposite, the non-ego or objective world, through pure spontaneous activity. This meant that what appeared to be external material reality was actually a product of spiritual activity, albeit unconscious spiritual activity, that created the appearance of independence and externality. The implications for simulation scenarios were striking. If reality was fundamentally mental in character, then the distinction between real and simulated experience might be a false dichotomy. All experience would be, in some sense, the product of mental activity, whether conscious or unconscious, individual or absolute. Schelling developed a philosophy of nature that proposed an underlying identity between mind and nature, consciousness and matter. The natural world was unconscious poetry, while consciousness was nature made transparent to itself. This identity philosophy suggested that the development of consciousness and the development of nature were two aspects of a single absolute process. Hegel's phenomenology traced the development of consciousness through increasingly sophisticated forms of self-awareness, culminating in absolute knowledge where the distinction between subject and object was finally overcome. The entire process of human history and natural development was understood as the self-development of absolute spirit coming to know itself through finite forms of consciousness. These idealist systems provided conceptual resources for thinking about reality in ways that transcended traditional distinctions between mental and material, subjective and objective, real and apparent. If reality was fundamentally spiritual in character, then questions about whether experience corresponded to an independent material world might be based on false assumptions about the nature of reality itself. 19th-century developments, science and consciousness. The 19th century witnessed explosive development in scientific understanding that provided new perspectives on the relationship between consciousness and physical reality. Advances in physics, chemistry, biology, and psychology suggested both the power and the limitations of scientific approaches to understanding the nature of experience. The wave theory of light, developed through the work of Thomas Young and Augustin Fresnel, revealed that what appeared to be solid reality was actually composed of wave-like disturbances in invisible media. The electromagnetic theory developed by James Clerk Maxwell showed that light, electricity, and magnetism were manifestations of a single underlying field that pervaded all space. These developments suggested that the ultimate constituents of physical reality might be very different from what they appeared to be in ordinary experience. The development of thermodynamics and statistical mechanics revealed that apparently solid matter was actually composed of vast numbers of tiny particles in constant motion. The behavior of gases could be understood statistically, even when the motion of individual particles remained unpredictable. This suggested that the regularities observed in macroscopic experience might emerge from underlying microscopic processes that followed different principles. Advances in physiology and psychology provided new understanding of the relationship between consciousness and brain activity. The work of Hermann von Helmholtz showed that perception involved active interpretation of sensory signals rather than passive reception of external information. Ernst Weber and Gustav Fechner developed psychophysics, which revealed mathematical relationships between physical stimuli and psychological responses. The discovery of unconscious mental processes through the work of figures like Carl Gustav Carus and Eduard von Hartmann suggested that consciousness might be only a small part of mental life. Much of what influenced human behavior and experience seemed to occur below the threshold of awareness, raising questions about the relationship between conscious experience and underlying mental reality. Charles Darwin's theory of evolution provided a naturalistic framework for understanding the development of consciousness and cognitive capacities. If human minds had evolved through natural selection, then their cognitive capacities should be understood in terms of their adaptive function rather than their capacity for achieving absolute truth. This evolutionary perspective suggested that the structure of human experience might reflect the requirements of biological survival rather than the ultimate nature of reality. The combination of these scientific developments created an intellectual context in which traditional assumptions about the relationship between consciousness and reality seemed increasingly problematic. The world revealed by scientific investigation was very different from the world of ordinary experience, suggesting that conscious experience might provide a systematically misleading guide to the nature of reality. Mathematics and the foundations of knowledge. The 19th century also witnessed revolutionary developments in mathematics that challenged traditional assumptions about logical and mathematical truth. The discovery of non-Euclidean geometries by Nikolai Lobachevsky, János Bolyai, and Carl Friedrich Gauss showed that the geometric principles that seemed obviously true to human intuition were not logically necessary. If parallel lines could meet, as in spherical geometry, or diverge, as in hyperbolic geometry, then the spatial structure of reality might be very different from what human experience suggested. The choice between different geometric systems could not be made on purely logical grounds, but required empirical investigation of the actual structure of physical space. The development of abstract algebra and set theory by figures like Évariste Galois, George Boole, and Georg Cantor revealed that mathematical reasoning could be applied to structures very different from those encountered in ordinary experience. Mathematics was not limited to the description of physical quantities, but could investigate any structures that exhibited formal relationships. The work of Cantor on infinite sets revealed paradoxes that challenged traditional logical principles. If the set of all sets that do not contain themselves as members contained itself, then it both did and did not contain itself. Such paradoxes suggested that even the most fundamental logical principles might need revision. These mathematical developments provided new resources for thinking about the relationship between formal systems and reality. If multiple geometric systems were internally consistent, and if logical principles themselves could be questioned, then the relationship between mathematical truth and physical reality became more complex than traditional philosophy had assumed. The stage was being set for 20th century developments that would give new life to the skeptical scenarios that had emerged from Cartesian doubt. The combination of scientific understanding of consciousness as a biological phenomenon, mathematical investigation of formal systems, and technological development of computational devices would create the context in which ancient philosophical questions would take on new forms and new urgency. By the end of the 19th century, the intellectual foundations were in place for a complete transformation of skeptical scenarios. The supernatural demons and divine minds of earlier philosophical speculation would be replaced by naturalistic possibilities that seemed genuinely achievable through technological development. The next century would witness the emergence of computational thinking that would give Cartesian doubt a technological form that its original author could never have imagined. Berkeley's immaterial revolution. But before we trace this technological transformation of ancient questions, we must return to examine more carefully the radical solution proposed by George Berkeley in early 18th century Ireland, where the father of modern philosophy had worried about distinguishing between real and apparent objects. Berkeley would argue that no such distinction was necessary, because there were no material objects to begin with. The world that seems so solid and independent of our minds, Berkeley proposed, exists only in being perceived. Reality itself in this audacious vision is fundamentally mental in character. Berkeley's transformation of the skeptical tradition represented one of the most dramatic philosophical turns in Western thought. Born in 1685 in Kilkenny, Ireland, to a family of modest means but respectable Anglican background, Berkeley came to philosophical maturity at Trinity College, Dublin, in an intellectual environment saturated with Cartesian themes and Newtonian science. The question of how finite minds could have reliable knowledge of an external material world had become central to philosophical discourse throughout Europe, creating an intellectual crisis that seemed to threaten the foundations of both natural philosophy and religious belief. The young Berkeley arrived at Trinity College in 1700, when he was barely 15 years old, a precocious student in an institution that prided itself on rigorous classical education and emerging scientific learning. Trinity College Dublin had embraced the new experimental philosophy with unusual enthusiasm for an Irish institution. The library contained the latest works of Isaac Newton, Robert Boyle, and John Locke, while the curriculum had been modified to include instruction in natural philosophy, alongside traditional studies in classics, theology, and mathematics. Berkeley's intellectual formation occurred during a period of remarkable cultural and political transformation in Ireland. The Williamite settlement following the Battle of the Boyne in 1690 had secured Protestant ascendancy, but left the island divided between a dominant English-speaking Protestant minority and a dispossessed Gaelic Catholic majority. This political context influenced Berkeley's philosophical development in subtle but significant ways, making him acutely aware of how different communities could inhabit radically different conceptual worlds while sharing the same geographical space. The philosophical environment at Trinity College was dominated by discussion of John Locke's essay concerning human understanding, which had been published just a decade before Berkeley's arrival. Locke had proposed that the mind knows external objects through ideas that represent them, but this representational theory immediately raised troubling questions that Berkeley would later identify as fatal to the entire empiricist program. If the mind has direct access only to its own ideas, Locke's critics argued, how could it ever determine whether those ideas accurately represented external material objects? The mind would be trapped behind what philosophers called the, quote, veil of perception, forever uncertain whether its internal states corresponded to external reality. This epistemological predicament provided the context for Berkeley's revolutionary solution. Berkeley's notebooks from his undergraduate years reveal a mind grappling with the fundamental problems of empiricist philosophy. Written in a mixture of Latin, English, and occasionally Irish Gaelic, these private philosophical reflections show the young Berkeley working through the implications of Locke's representational theory and discovering its internal contradictions. The crucial insight that would define Berkeley's mature philosophy emerged during his fellowship years at Trinity College, between 1707 and 1713. Berkeley's solution was as elegant as it was shocking. Eliminate the problematic material objects entirely. If the source of skeptical doubt lay in the unbridgeable gap between mental ideas and material things, then closing that gap by identifying ideas with things would solve the problem at a stroke. This was the revolutionary insight crystallized in Berkeley's famous principle, esse e percipi, to be is to be perceived. The audacity of this proposal can hardly be overstated. Berkeley was suggesting that the solid earth beneath our feet, the stars wheeling overhead in their courses, the very bodies we inhabit, all of these exist only as ideas in minds. There's no material substrate underlying sensory qualities, no hidden essence supporting the appearances that constitute our everyday experience. When we perceive what we call a tree, Berkeley argued, we are perceiving a systematically related collection of visual, tactile, and other sensory qualities that constitute the tree's entire being. The systematic argument against material substance. Berkeley's arguments for this extraordinary metaphysics were both sophisticated and systematic, developed through a series of works that began with his essay Towards a New Theory of Vision in 1709, and culminated in his Principles of Human Knowledge in 1710 and 3 dialogues between Hylas and Philanus in 1713. 1713. Each work approached the problem from a different angle, but all converged on the same revolutionary conclusion. Berkeley began by noting that sensory qualities like colors, sounds, tastes, and smells are clearly mind-dependent. The sweetness of sugar exists only in relation to creatures capable of tasting. The warmth of fire exists only in relation to beings capable of feeling temperature. The redness of roses exists only in relation to minds equipped with appropriate visual capabilities. This much seemed uncontroversial to most empiricist philosophers, who distinguished between secondary qualities that existed only in perception and primary qualities that belonged to objects themselves. But if these so-called secondary qualities are mind-dependent, Berkeley asked, with relentless logical precision, what grounds do we have for thinking that primary qualities, like extension, figure, and motion, are any different? The distinction between primary and secondary qualities crumbled under Berkeley's systematic analysis. Extension cannot be conceived apart from color or some other visible quality. Figure cannot be separated from the sensory modalities through which it is apprehended. Motion is always the motion of something that appears to some sense. The argument gained force through Berkeley's careful phenomenological analysis. When we attempt to conceive of material objects existing independently of all perception, we inevitably find ourselves imagining them being perceived by ourselves or by some other mind. The very attempt to think of unperceived objects demonstrates the impossibility of conceiving matter as it would exist apart from all perception. Berkeley's analysis of abstract ideas provided another line of argument against material substance. Following Locke's account, philosophers had supposed that the mind could form abstract general ideas, such as the idea of triangularity in general, apart from any particular triangle. Berkeley argued that such abstract ideas were impossible. The mind could think of particular triangles and notice their similarities, but it could not form an idea of triangularity that was neither scalene nor isosceles, neither large nor small, neither this color nor that. If abstract ideas were impossible, then the entire framework of material substance collapsed. Material substance was supposed to be the abstract substrate that supported particular qualities without being identical to any particular collection of qualities. But if such abstraction was impossible, then the notion of material substance was incoherent. The theological solution to continuity. Berkeley's idealism thus emerged not from mystical intuition, but from rigorous empirical analysis. If all human knowledge derives from sensory experience, as empiricist philosophers maintained, then we can have no knowledge of anything that transcends the realm of possible experience. Material substance, being by definition imperceptible and unknowable, falls outside the bounds of any coherent empirical philosophy. Yet Berkeley's idealism raised new puzzles of its own. If objects are collections of ideas, and ideas exist only when perceived, how can we account for the apparent continuity and independence of the external world? When Berkeley left his study and returned later to find his books exactly where he had left them, what accounted for their persistence during his absence? Berkeley's theological solution required God to serve as the ultimate perceiver whose infinite awareness sustains every aspect of the phenomenal world with perfect consistency. Divine perception guaranteed the regularity and independence that made the natural world suitable for rational investigation and practical action. God's infinite mind contained the archetypal ideas that served as patterns for the ideas perceived by finite minds, ensuring that different perceivers could share a common world of experience. This theological framework transformed the problem of skepticism into a problem of divine reliability. Rather than worrying about whether finite minds could achieve knowledge of an independent material world, Berkeley's idealism made the question turn on whether God could be trusted to maintain consistent patterns in the ideas He causes finite minds to perceive. Since God's perfect goodness and wisdom guaranteed the reliability of divine activity, Berkeley argued, finite minds could have complete confidence in the regularity and intelligibility of natural experience. The theological solution also provided an elegant account of natural laws. Rather than describing the behavior of material particles acting according to mechanical forces, natural laws described the regular patterns according to which God chose to cause ideas in finite minds. The law of gravitation, for instance, described not the attraction between material masses, but the systematic way in which God caused ideas of motion in response to ideas of spatial proximity, the cultural reception, and philosophical implications. Berkeley's contemporaries found his philosophical conclusions almost impossible to accept. Samuel Johnson famously refuted Berkeley by kicking a stone, as if the painful sensation proved the existence of material objects. Critics accused Berkeley of philosophical sophistication that contradicted common sense and practical experience. Yet Berkeley insisted that his philosophy supported, rather than undermined, common sense. Ordinary people believed in the reality of trees, stones, and other perceived objects. Berkeley's idealism affirmed this reality while simply clarifying that such objects existed as ideas in minds rather than as material substances beyond all possible perception. The practical implications remained the same. Trees could provide shade, stones could cause pain, and fire could burn. The philosophical implications of Berkeley's idealism extended far beyond epistemological questions about knowledge and skepticism. If reality was fundamentally mental in character, then consciousness rather than matter constituted the basic furniture of the universe. This reversed the materialist assumption that mind emerged from matter through complex physical processes, suggesting instead that apparent material processes emerged from underlying mental reality. Berkeley's idealism also provided a new framework for thinking about personal identity and the relationship between finite and infinite minds. If individual minds were essentially spiritual substances, capable of perceiving ideas, then personal identity could survive the destruction of any associated material body. Death would involve not the cessation of consciousness, but its translation to a different regime of divine ideas. The social and political implications of Berkeley's idealism were complex and sometimes surprising. On one hand, the doctrine seemed to support religious orthodoxy by making divine activity central to natural experience. On the other hand, it challenged traditional assumptions about the relationship between spiritual and temporal authority by suggesting that material wealth and power were ultimately illusory. Berkeley's later career as Anglican Bishop of Cloyne in Ireland saw him attempt to work out the practical implications of his philosophical idealism. His interests in social reform, economic development, and educational innovation reflected his conviction that philosophical truth should transform practical life. The same intellectual rigor that had led him to dissolve material substance drove his efforts to improve the conditions of life for ordinary Irish people. Idealism and the anticipation of simulation scenarios. From the perspective of contemporary debates about simulation theory, Berkeley's idealism appears remarkably prescient. His vision of reality as fundamentally consisting in the systematic production of experiences by a supremely intelligent being anticipated key features of computational simulation scenarios. The main difference lay in substituting divine mind for computer technology as the source of systematic experience. Berkeley's God possessed capabilities that closely parallel those attributed to the advanced civilizations of Bostrom's simulation argument. Divine omniscience ensured perfect knowledge of how to create convincing experiences. Divine omnipotence provided unlimited computational resources. Divine omnipresence allowed real-time responsiveness to the thoughts and actions of finite perceivers. The theological framework also anticipated some of the puzzles that arise in contemporary simulation theory. If simulated beings could achieve genuine knowledge and moral development within their simulated environment, what would be the ethical status of creating and terminating simulations? Berkeley's theology suggested that simulated beings, from the perspective of divine idealism, all finite beings, possessed genuine moral status and deserved consideration in divine providential planning. The epistemological implications of Berkeley's idealism also anticipated contemporary discussions about the relationship between simulated and non-simulated experience. If the criteria for distinguishing between genuine and illusory experience had to be drawn from within experience itself, then no absolute distinction could be maintained. What mattered was not the ultimate metaphysical status of experience, but its internal coherence, predictability, and moral significance. Berkeley's philosophy thus provided conceptual resources for thinking about simulation scenarios that went beyond the purely skeptical framework inherited from Cartesian doubt. Rather than treating the possibility of systematic deception as a threat to knowledge and meaning, Berkeley's idealism suggested ways in which simulated experience could be genuinely real and morally significant. The transition from Berkeley's theological idealism to contemporary computational scenarios would require centuries of development in mathematics, logic, and technology. But the conceptual framework for thinking about reality as fundamentally consisting in the systematic production of experience by intelligence, whether divine or artificial, had been established by the early 18th century in the quiet studies of Trinity College Dublin. Putnam's technological revolution. The most striking development in the evolution of skeptical scenarios would not occur until the late 20th century, when advances in computer science and cognitive psychology gave new life to ancient philosophical puzzles. The figure who would prove most influential in this transformation was an American philosopher named Hilary Putnam, who in 1981 proposed a modernized version of Cartesian skepticism that seemed precisely tailored to an age of increasingly sophisticated computational technology. The intellectual context in which Putnam developed his brain-inovat scenario was shaped by remarkable convergences in multiple fields of inquiry. The 1970s and early 1980s witnessed explosive growth in computer science, artificial intelligence research, and cognitive psychology that made computational approaches to understanding mind and reality seem both theoretically compelling and practically achievable. The technological context of computational skepticism. The emergence of digital computers during the mid-20th century had initially seemed like a purely practical development with limited philosophical implications. Early machines like ENIAC and UNIVAC were designed for specific computational tasks, calculating artillery trajectories, processing census data, performing complex mathematical operations that would be tedious for human calculators. But as computational power increased and programming techniques became more sophisticated, researchers began to recognize that computers might provide new models for understanding intelligence itself. The development of artificial intelligence as a research program during the 1950s and 1960s transformed computational machines from mere calculators into potential minds. Pioneering researchers like Alan Turing, John McCarthy, and Marvin Minsky argued that intelligent behavior could be understood as the manipulation of symbols according to formal rules, precisely the kind of activity that digital computers performed with increasing sophistication. Turing's famous 1950 paper Computing Machinery and Intelligence had proposed what became known as the Turing test. If a machine could engage in conversations indistinguishable from those of intelligent humans, there would be no principled basis for denying that the machine was genuinely intelligent. This criterion suggested that intelligence was defined by behavioral capacities, rather than by the specific material substrate that supported those capacities. The implications for skeptical scenarios were profound. If intelligence could be substrate-independent, then consciousness might be similarly independent of its particular physical implementation. A sufficiently sophisticated computer could, in principle, support conscious experience that was phenomenologically indistinguishable from biological consciousness. The 1970s saw dramatic advances in computer graphics and simulation technology that made the idea of comprehensive experiential deception seem increasingly plausible. Early video games like Pong and Space Invaders were primitive by later standards, but they demonstrated that electronic systems could create immersive visual experiences that engaged users' attention and emotional responses. Flight simulators developed for pilot training showed how computer-generated environments could provide realistic experiences of complex dynamic systems. Simultaneously, advances in neuroscience were revealing the computational character of biological information processing. Researchers discovered that neurons functioned essentially as biological computers, integrating multiple inputs according to mathematical functions and generating outputs that influenced other neural networks. The brain appeared to be a massively parallel biological computer that processed information about the environment and generated appropriate behavioral responses. The brain in a Bas scenario. Putnam's innovation was to replace Descartes' supernatural demon with a naturalistic scenario that seemed almost technologically feasible. Instead of imagining a malevolent supernatural being, Putnam asked readers to consider the possibility that they were brains in a vat, disembodied neural organs, suspended in life-supporting fluid, and connected to a sophisticated computer that supplied all their sensory experiences. The scenario gained its philosophical power from its apparent scientific plausibility. Neuroscientists had demonstrated that electrical stimulation of specific brain regions could trigger vivid sensory experiences. Patients undergoing brain surgery under local anesthesia reported seeing lights, hearing sounds, or feeling tactile sensations when surgeons stimulated particular neural areas. If such localized stimulation could produce specific experiences, then comprehensive stimulation might produce comprehensive experience. This computer would be programmed to generate experiences that felt exactly like those of embodied human beings living in a normal physical environment. The envatted brain would experience itself as having a body, as inhabiting a world of objects, as interacting with other people. But all of these experiences would be computational illusions with no basis in external reality. The technological requirements for such a system pushed against the boundaries of what seemed possible, but not beyond them entirely. The computer would need to maintain detailed models of physical environments, track the consequences of the brain's apparent actions, and generate appropriate sensory feedback in real time. But advances in computer simulation and virtual reality suggested that such capabilities might eventually become available. The scenario's cultural resonance reflected broader anxieties about the relationship between human experience and technological mediation. The 1970s and 1980s saw the emergence of personal computers, video games, and early forms of computer networking that began to mediate significant portions of human experience. People were spending increasing amounts of time interacting with computational systems rather than directly with physical environments and other people. Semantic externalism and the self-refuting argument. But Putnam's real innovation lay not in formulating this skeptical scenario, but in arguing that it was necessarily false. Drawing on his work in philosophy of language and mind, Putnam contended that the statement, "I am a brain in a vat," could not be true when uttered by a brain in a vat. The argument turned on semantic externalism, the theory that the meanings of our words and thoughts depend partly on our causal environment rather than solely on our internal mental states. The development of semantic externalism during the 1970s represented a significant departure from traditional approaches to meaning and reference. Earlier philosophical theories had assumed that the meaning of a word was determined by the mental concepts or ideas associated with it by speakers. Putnam's twin earth thought experiment suggested that meaning depended not just on internal mental states but on the external environment in which those states were embedded. Consider Putnam's famous example. Twin earth is exactly like Earth, except that the substance that fills lakes and rivers and that twin earthers call water has the chemical composition XYZ rather than H2O. When an earth person says water, they refer to H2O. When a twin earth person says water, they refer to XYZ. This difference in reference occurs despite the fact that Earth and twin earth people might have identical internal mental states when thinking about water. According to Putnam's argument, a brain that had always been in a vat would have no causal contact with real brains or real vats. When such a brain used words like brain and vat, these words would refer not to actual brains and vats but to whatever objects in the simulated environment had played the causal role that brains and vats played in the program. The unvatted brain would be like the twin earth person who uses the word water to refer to XYZ rather than H2O. When the unvatted brain said, "I am a brain in a vat," the words brain and vat would refer to simulated brains and vats within the computer program rather than to the actual brain and vat that constituted its physical situation. Philosophical implications and critical responses. Putnam's argument was philosophically ingenious, but it also generated extensive critical discussion that revealed both its power and its limitations. Critics noted that the argument seemed to work only for brains that had always been in vats, not for recently invatted brains that retained their original linguistic competence. A person who had grown up in the normal world and then been placed in a vat would presumably retain the ability to refer to real brains and vats. Moreover, the argument seemed to rely on controversial claims about the nature of meaning and reference that many philosophers found questionable. The causal theory of reference that supported Putnam's argument competed with other approaches to meaning that might not yield the same anti-skeptical conclusions. Some critics argued that Putnam's argument proved too much. If semantic externalism made it impossible for invatted brains to refer to their actual situation, then it might also make it impossible for normal people to refer to skeptical scenarios. This would make the brain in a vat hypothesis meaningless rather than false, which seemed to miss the point of the skeptical challenge. The argument also raised questions about the relationship between truth and knowledge. Even if invatted brains could not truly say that they were brains in vats, this did not necessarily mean that they could know that they were not brains in vats. The semantic argument might establish metaphysical conclusions about truth and reference, without resolving epistemological questions about knowledge and justification. The cultural impact of computational skepticism. Despite these philosophical complexities, Putnam's brain in a vat scenario captured the imagination of both philosophers and the broader culture in ways that earlier skeptical scenarios had not. The scenario appeared in science fiction novels, films, and television shows that explored the implications of advanced computational technology for human experience and identity. The scenario's cultural influence reflected its apparent technological plausibility during a period of rapid advancement in computer science and neuroscience. Unlike Descartes' evil demon or Berkeley's divine perceiver, Putnam's scenario seemed like something that might actually be achievable through technological development, rather than requiring supernatural intervention. The emergence of virtual reality systems during the 1980s and 1990s made the basic idea of computer-generated sensory experience increasingly familiar. Early VR systems like those developed by Jaron Lanier and VPL Research provided crude but convincing demonstrations that computers could create immersive visual and auditory experiences that engaged users' attention and emotional responses. The development of the Internet and personal computing during the same period transformed the relationship between human experience and digital mediation. People began conducting significant portions of their social, economic, and intellectual lives through computational interfaces. The boundary between real and virtual experience became increasingly blurred as digital environments provided genuine sources of meaning, satisfaction, and identity. Computational philosophy of mind. Putnam's scenario also contributed to broader developments in computational approaches to understanding consciousness and cognition. The functionalist philosophy of mind that emerged during the 1960s and 1970s proposed that mental states should be understood in terms of their causal roles rather than their physical substrates. According to functionalist theories, what made something a belief or desire or sensation was not its particular physical implementation, but its pattern of causal relationships with inputs, outputs, and other mental states. This suggested that consciousness could, in principle, be realized in any physical system that supported the appropriate pattern of causal relationships, including digital computers. The computational theory of mind proposed that thinking was essentially the manipulation of symbolic representations according to formal rules. This made consciousness analogous to software running on the hardware of the brain. If this analogy was correct, then consciousness could potentially be transferred from biological to artificial substrates without loss of essential characteristics. These developments in philosophy of mind provided theoretical frameworks for thinking about brain-in-a-vat scenarios that went beyond purely epistemological questions about knowledge and skepticism. If consciousness was substrate-independent, then the experiences of envatted brains might be as real and valuable as those of normally embodied people. The convergence of computational technology, neuroscientific understanding, and functionalist philosophy created an intellectual context in which skeptical scenarios seemed both more plausible and more relevant than they had in earlier periods. The questions raised by Cartesian doubt were no longer merely abstract philosophical puzzles, but practical challenges that might need to be addressed as technology continued to develop. By the end of the 20th century, the conceptual foundations were in place for an even more systematic and influential treatment of simulation scenarios. The technological context that made Putnam's arguments compelling would provide the background for philosophical arguments that shifted attention from logical possibility to empirical probability, arguments that would transform ancient skeptical themes into contemporary scientific hypotheses. Bostrom's probabilistic revolution. The transformation would reach its most systematic expression in 2003, when Swedish philosopher Nick Bostrom published a paper that would revolutionize the simulation debate by shifting attention from the logical possibility of skeptical scenarios to their empirical probability. Bostrom's innovation was profound. Instead of asking whether we could know for certain that we are not in a simulation, he asked what the odds might be that we actually are in one. The intellectual context in which Bostrom developed his simulation argument reflected the convergence of several distinct but related developments in early 21st century thought. Advances in computer science had made digital simulation increasingly powerful and ubiquitous. Moore's law, the observation that computational capacity doubled approximately every 2 years, suggested that current trends in technological development might continue for decades, potentially reaching levels that seemed almost unimaginable from the perspective of earlier generations. The cultural context of exponential growth. The late 1990s and early 2000s witnessed an unprecedented acceleration in the development of digital technologies that made simulation scenarios seem increasingly plausible. The emergence of the World Wide Web had connected billions of people through digital networks that mediated growing portions of human social, economic, and intellectual activity. Online communities formed around shared interests that transcended geographical boundaries. Virtual economies within computer games generated real economic value that could be exchanged for conventional currencies. Personal computers had evolved from specialized tools used by technical experts to ubiquitous consumer devices that shaped daily life for hundreds of millions of people. Video game graphics had progressed from simple geometric shapes to photorealistic renderings that could create compelling illusions of three-dimensional environments. Early massively multiplayer online games like Ultima Online and EverQuest demonstrated that thousands of people could share persistent virtual worlds that provided genuine sources of meaning, identity, and social connection. The Human Genome Project had been completed in 2003, the same year Bostrom published his simulation argument, providing a complete map of human genetic information that seemed to bring the artificial creation of life within the realm of technological possibility. Advances in neuroscience were revealing the computational principles that governed brain function, suggesting that consciousness itself might eventually be understood well enough to be artificially replicated. The cultural atmosphere of the early 2000s was characterized by what observers called technological optimism or techno-utopianism, a widespread belief that exponential technological progress would solve most human problems and open unprecedented possibilities for human enhancement and expansion. This optimism provided the background assumptions that made Bostrom's simulation argument seem both plausible and significant. The simulation argument's logical structure. Bostrom's simulation argument took the form of an elegant trilemma, an argument showing that at least one of three propositions must be true. First, that human civilization is very likely to go extinct before reaching technological maturity. Second, that technologically mature civilizations are extremely unlikely to run computer simulations of their evolutionary history. And third, that we are almost certainly living in a computer simulation. The logical structure of this argument was both simple and profound. Bostrom was not arguing that we are definitely living in a simulation, but rather that our evidence about technological development and civilizational behavior implied that at least one of three claims must be true. The argument forced readers to choose between accepting a pessimistic view of human survival prospects, a surprising claim about the behavior of advanced civilizations, or a radical conclusion about the nature of our own reality. The first horn of the trilemma reflected widespread concerns about existential risks to human civilization. Nuclear weapons, climate change, ecological collapse, pandemics, and other global catastrophic risks might prevent human civilization from reaching technological maturity. If most civilizations destroyed themselves or encountered insurmountable obstacles before developing advanced computational capabilities, then the simulation argument would not apply to them. The second horn suggested that technologically mature civilizations might choose not to run ancestor simulations despite having the capability to do so. Perhaps such simulations would be considered unethical because they involved creating conscious beings who might suffer. Perhaps advanced civilizations would lose interest in their evolutionary history and focus their computational resources on other projects. Perhaps there would be fundamental physical limits that made large-scale simulation impractical, even for very advanced technologies. The third horn, that we are almost certainly living in a computer simulation, followed from the rejection of the first two possibilities. If human civilization survived to technological maturity and chose to run ancestor simulations, then the number of simulated human beings would vastly exceed the number of non-simulated ones. Statistical reasoning would then suggest that any randomly selected human being would be more likely to be simulated than real. The mathematics of simulation multiplicity. The mathematical reasoning behind Bostrom's argument depended on assumptions about the computational capabilities that might be available to technologically mature civilizations. If such civilizations could run detailed simulations of human history with conscious simulated beings, they would likely run many such simulations for various scientific, educational, or entertainment purposes. Bostrom estimated that the computational requirements for simulating human brains might be achievable using technologies that were advanced but not physically impossible. If Moore's law continued for several more decades, digital computers might achieve computational capacities comparable to biological brains. If quantum computing or other exotic computational paradigms proved feasible, even greater computational resources might become available. The argument assumed that technologically mature civilizations would have access to computational resources that vastly exceeded those available to contemporary human civilization. A single advanced civilization might be able to run thousands or millions of detailed ancestor simulations, each containing billions of conscious simulated beings living complete simulated lives. From a statistical perspective, this created what Bostrom called the simulation multiplicity effect. If the ratio of simulated to non-simulated beings was very large, then the probability that any particular conscious being was simulated rather than non-simulated would approach unity. The more simulations an advanced civilization chose to run, the more confident we could be that we ourselves were simulated. This statistical reasoning represented a significant departure from traditional approaches to skeptical scenarios. Rather than focusing on logical possibility or epistemological certainty, Bostrom's argument treated the simulation hypothesis as an empirical claim that could be evaluated using probabilistic reasoning and inductive inference. Technological projections and computational limits. The plausibility of Bostrom's argument depended crucially on assumptions about the computational requirements for consciousness and the technological capabilities that might be available to advanced civilizations. These assumptions pushed against the boundaries of current scientific understanding while remaining within the realm of physical possibility. Contemporary neuroscience suggested that consciousness emerged from the electrochemical activity of networks of neurons in biological brains. If consciousness was substrate independent, as functionalist theories of mind proposed, then it might be possible to create conscious experiences using silicon-based computers, rather than carbon-based biological systems. Estimates of the computational requirements for simulating human brains varied widely depending on the level of detail required. Simulating every molecule in a human brain would require computational resources that seemed prohibitively expensive even for very advanced civilizations. But simulating the functional behavior of neural networks might require significantly fewer computational resources while still supporting conscious experience. The argument also depended on assumptions about technological development that extrapolated from current trends without accounting for possible physical limits or practical constraints. Moore's law might not continue indefinitely. Quantum mechanical effects might impose fundamental limits on miniaturization. Energy requirements might make large-scale simulation impractical even for advanced civilizations. Cultural resonance and philosophical implications. Bostrom's argument gained unusual cultural prominence because it seemed to provide a rigorous philosophical framework for anxieties that were already widespread in early 21st century technological culture. Science fiction films like The Matrix had popularized the idea that reality might be a computer simulation, while the rapid development of virtual reality systems made such scenarios seem increasingly plausible. The argument resonated with broader concerns about the relationship between human identity and technological mediation. If increasing portions of human experience were mediated by computational systems, what distinguished real from artificial experience? If virtual environments could provide genuine sources of meaning and satisfaction, why should the ultimate metaphysical status of those environments matter? The simulation argument also connected with philosophical discussions about the nature of consciousness and personal identity that had been developing throughout the 20th century. If consciousness was functionally defined rather than tied to specific biological substrates, then simulated beings might have the same moral status as non-simulated ones. This raised profound ethical questions about the creation and termination of simulations. If simulated beings were genuinely conscious, then creating simulations would involve bringing conscious beings into existence, while terminating simulations would involve destroying them. Advanced civilizations would need to consider the moral implications of their computational activities. Critical responses and refinements. Bostrom's argument generated extensive philosophical discussion that revealed both its strengths and its limitations. Critics pointed to potential flaws in the statistical reasoning, questionable assumptions about technological development, and alternative interpretations of the evidence that the argument was supposed to explain. Some critics argued that the reference class problem undermined the statistical reasoning. When calculating the probability that we are simulated, should we consider all conscious beings, all human-like beings, all beings in our specific historical situation, or some other reference class? Different choices might yield different probability estimates. Others questioned whether conscious simulated beings would really be as numerous as the argument suggested. Perhaps advanced civilizations would simulate only the decision-making processes of historical figures, rather than the detailed conscious experiences of entire populations. Perhaps most simulated beings would be philosophical zombies, behaviorally identical to conscious beings, but lacking subjective experience. The technological assumptions underlying the argument also attracted criticism. Some critics argued that the computational requirements for consciousness were much higher than Bostrom had estimated, making large-scale simulation impractical even for very advanced civilizations. Others suggested that physical laws might impose fundamental limits on computation that would prevent the kind of technological development that the argument required. The doomsday argument connection. Bostrom's simulation argument shared logical structure with other philosophical arguments that used statistical reasoning to draw surprising conclusions about human survival and cosmic significance. The doomsday argument, developed by Brandon Carter and others, used similar probabilistic reasoning to suggest that human extinction might be more likely than commonly assumed. These arguments reflected a broader trend in contemporary philosophy toward using formal methods borrowed from probability theory, decision theory, and game theory to address traditional philosophical questions. Rather than relying solely on conceptual analysis or intuitive reasoning, philosophers were increasingly incorporating mathematical tools that allowed more precise formulation of arguments and objections. The connection between simulation arguments and other probabilistic arguments about human significance suggested that our intuitive assumptions about our place in the cosmos might be systematically misleading. If we were typical observers in a universe containing many observers, then our evidence about technological development and civilizational behavior might support surprising conclusions about the nature of reality. The transformation of skeptical tradition. Bostrom's argument represented the culmination of a philosophical tradition that began with Descartes' evil demon and evolved through Berkeley's idealism and Putnam's technological scenarios. Each generation had brought new conceptual resources to bear on fundamental questions about the relationship between consciousness and reality, but Bostrom's contribution was distinctive in its systematic use of probabilistic reasoning. Where earlier skeptical arguments had focused on logical possibility, could we be systematically deceived? Bostrom's argument focused on empirical probability. How likely is it that we are systematically deceived? This shift reflected broader changes in philosophical methodology that emphasized the importance of empirical evidence and inductive reasoning in addressing traditionally metaphysical questions. The argument also reflected the increasing integration of philosophical and scientific approaches to understanding consciousness and reality. Rather than treating skeptical scenarios as purely abstract logical possibilities, Bostrom's argument drew on empirical claims about technological development, computational theory, and the physical requirements for consciousness. By the early 21st century, the ancient questions raised by Cartesian doubt had been transformed into contemporary scientific hypotheses that could potentially be tested through empirical investigation. The simulation argument represented not the end of skeptical thinking, but its transformation into a research program that connected philosophical reflection with scientific inquiry and technological development. Contemporary challenges and scientific constraints. Even as Bostrom's argument gained cultural prominence, it also attracted scientific criticism that revealed important limitations in the simulation hypothesis. Some critics focused on computational constraints, arguing that the amount of computing power required to simulate a universe would exceed what was physically possible even for advanced civilizations. The most systematic recent challenge has come from astrophysicists who have attempted to calculate the actual energy requirements for running universe-scale simulations. Franco Vazza, working at the University of Bologna, published research in 2025 showing that simulating even a single planet like Earth would require energy equivalent to the binding energy of the Milky Way galaxy. Simulating the entire observable universe would require converting more mass energy than exists within the universe itself into computational resources. Thermodynamic constraints on computation. Vazza's calculations drew on sophisticated understanding of the relationship between information and energy in physical systems. The fundamental principle underlying these constraints is Landauer's principle, which establishes that erasing one bit of information requires a minimum energy expenditure of kT ln 2, where K is Boltzmann's constant, and T is the absolute temperature of the system. This seemingly modest requirement becomes overwhelming when scaled to the information processing demands of realistic simulations. Consider the computational requirements for simulating a single human brain, which contains approximately 86 billion neurons, each connected to thousands of others through synaptic junctions. If we assume that each neuron can be modeled as a simple computational unit that processes information at rates comparable to biological neurons, the brain would require roughly 10 to the power of 15 operations per second to simulate accurately. Extending this calculation to simulate the brains of Earth's entire human population would require approximately 8 times 10 to the power of 25 operations per second. But consciousness and intelligent behavior emerge not merely from isolated brains but from the complex interactions between brains and their environments. Simulating convincing human experience would require modeling the physical environments in which simulated humans appear to live, the objects with which they interact, and the other people with whom they communicate. The computational requirements expand exponentially as the scope of simulation increases. The holographic principle, emerging from theoretical physics research on black holes and quantum gravity, implies that the amount of information that can be processed in any region of space is fundamentally limited by the area of that region's boundary rather than its volume. This places strict upper bounds on the computational capacity of any physical system, regardless of how advanced its technology might be. When applied to simulation scenarios, these holographic bounds suggest that simulating a region of space requires computational resources that scale with the boundary area of that region. For large-scale simulations, the computational resources required would approach or exceed the total information processing capacity of the region being simulated, making the simulation physically impossible even in principle. Quantum mechanics and computational complexity. The quantum mechanical nature of physical reality introduces additional complications for simulation scenarios. Classical computers operate by manipulating discrete bits of information that can be in either of two definite states. Quantum systems exist in superpositions of multiple states simultaneously, and their behavior is governed by probability amplitudes rather than definite classical properties. Simulating quantum systems on classical computers requires exponentially increasing computational resources as the number of quantum particles grows. A quantum system containing just 300 particles would require more classical computational states than there are atoms in the observable universe to simulate accurately. This suggests that realistic simulations of macroscopic quantum systems may be computationally intractable even for arbitrarily advanced classical computers. Quantum computers might, in principle, be able to simulate quantum systems more efficiently than classical computers. But quantum computers are themselves physical systems subject to the same thermodynamic and holographic constraints that limit classical computation. They cannot violate fundamental physical laws that relate information processing to energy expenditure and spatial organization. The phenomenon of quantum decoherence presents additional challenges for simulation scenarios. Quantum systems naturally lose their quantum coherence through interactions with their environments, transitioning from quantum superpositions to classical definite states. Maintaining quantum coherence in large-scale quantum computers requires sophisticated error correction techniques that consume additional computational resources. Alternative simulation strategies. Recognition of these physical constraints has led some researchers to propose alternative simulation strategies that might be more computationally feasible while still supporting the essential features of Bostrom's argument. Rather than simulating entire universes down to the quantum level, advanced civilizations might focus on simulating only those aspects of reality directly relevant to the conscious experience of simulated beings. One possibility is procedural generation of simulated environments, where detailed simulations are created only when and where they are needed to support conscious experience. A simulated person looking at a distant mountain would trigger the generation of appropriate visual details for that mountain, but the mountain's internal structure would remain uncomputed unless the simulated person actually traveled there and examined it closely. This approach would dramatically reduce computational requirements by avoiding unnecessary calculations, but it would also introduce potential inconsistencies that might be detectable by careful observation. If simulated beings develop sufficient scientific understanding, they might be able to detect the boundaries between computed and uncomputed regions of their simulated reality. Another possibility is lossy compression of simulated reality, where approximations replace exact calculations whenever the differences would not be detectable by simulated conscious observers. Human perception has limited resolution in space, time, and other dimensions, so simulations might exploit these limitations to reduce computational requirements without affecting subjective experience. The effectiveness of such compression techniques would depend on detailed understanding of the computational requirements for consciousness and the limits of conscious observation. If consciousness required exact quantum mechanical calculations, then lossy compression might not be feasible. If consciousness emerged from higher-level patterns that were relatively insensitive to microscopic details, then substantial compression might be possible. Future physics and computational possibilities. The constraints imposed by contemporary physics might not represent absolute limits on computational capability. Future developments in theoretical physics might reveal new computational paradigms that transcend current limitations, just as quantum mechanics revealed possibilities that were inconceivable from the perspective of classical physics. Speculative possibilities include computation using exotic matter with negative energy density, computation using closed time-like curves that exploit the structure of space-time itself, or computation using parallel universes in many worlds interpretations of quantum mechanics. Such possibilities remain highly speculative and may prove to be physically impossible, but they illustrate the difficulty of placing absolute limits on technological capability. The development of artificial intelligence systems that exceed human cognitive capabilities might also transform our understanding of consciousness and computation. If advanced AI systems achieved forms of consciousness very different from human consciousness, they might discover computational techniques for creating conscious experience that are much more efficient than biological mechanisms. Research in neuroscience continues to reveal the computational principles underlying biological consciousness, potentially providing blueprints for more efficient artificial implementations. If consciousness emerges from specific patterns of information processing rather than from particular biological substrates, then it might be possible to create conscious experience using computational resources much smaller than those required to simulate complete biological brains. Philosophical synthesis, contemporary relevance. The persistence of simulation-related themes across nearly 4 centuries of philosophical development suggests that something more than technological contingency is at stake in these debates. The skeptical challenge represented by Descartes' evil demon, Berkeley's idealism, Putnam's brain in a Vat scenario, and Bostrom's simulation argument points toward fundamental questions about the nature of consciousness, knowledge, and reality that cannot be easily dissolved through either philosophical argument or scientific discovery. At the deepest level, these scenarios force us to confront the apparent gap between conscious experience and objective reality. We have immediate access to our thoughts, sensations, and perceptions, but we lack similarly direct access to the world beyond consciousness. This veil of perception creates conceptual space for the possibility that experience might be systematically misleading about the nature of reality. Digital culture and the actualization of philosophical scenarios. The contemporary relevance of these classical philosophical themes becomes apparent when we consider how digital technology is increasingly mediating human experience. We live in an age of social media platforms, virtual meetings, augmented reality systems, and immersive gaming environments that create experiences which are simultaneously artificial and phenomenologically compelling. Young people growing up in the early 21st century report forming meaningful relationships with digital characters in video games, developing emotional attachments to online personas, and deriving genuine satisfaction from achievements in virtual worlds. Professional esports players earn substantial incomes competing in simulated environments, while virtual economies generate billions of dollars in real economic value. The boundary between real and simulated experience is becoming increasingly blurred in ways that give new urgency to questions that philosophers have been asking for centuries. When a person spends 8 hours each day working in virtual environments, socializes primarily through digital platforms, and finds their deepest sources of meaning in online communities, in what sense can we distinguish between their real and virtual experiences? Social media platforms like Facebook, Instagram, and TikTok create carefully curated versions of reality that shape users' perceptions of social norms, political opinions, and personal relationships. Algorithmic recommendation systems determine which information users encounter, potentially creating personalized information bubbles that bear little resemblance to objective social reality. The phenomenon of filter bubbles and echo chambers in digital media represents a technological actualization of Berkeley's idealism. Users inhabit information environments that are systematically constructed by algorithms designed to maximize engagement rather than accuracy. The reality presented by these platforms consists largely of patterns of information designed to capture and maintain attention, much like Berkeley's ideas designed to maintain coherent experience. Virtual and augmented reality systems are approaching the technological sophistication needed to create genuinely convincing alternative realities. Contemporary VR headsets can create visual and auditory experiences that engage users' attention for hours at a time, while haptic feedback systems provide increasingly sophisticated tactile sensations. Brain-computer interfaces under development might eventually bypass sensory organs entirely, stimulating neural activity directly to create conscious experiences indistinguishable from those produced by natural perception. Consciousness studies and neuroscience integration. Advances in neuroscience and artificial intelligence are providing new perspectives on the relationship between consciousness and its physical substrates. Brain imaging technologies reveal the neural correlates of specific conscious experiences, showing how changes in brain activity correspond to changes in subjective experience. These discoveries support functionalist theories of mind that treat consciousness as a pattern of information processing rather than as a property of specific biological materials. The development of large language models like GPT-3 and GPT-4 has demonstrated that artificial systems can exhibit sophisticated linguistic behavior that appears to require genuine understanding. These systems can engage in conversations, answer questions, write poetry, and solve problems in ways that seem to demonstrate comprehension and creativity. While debates continue about whether such systems are genuinely conscious, their capabilities challenge traditional assumptions about the uniqueness of human intelligence. Research in cognitive science reveals that much of what we experience as reality is actively constructed by neural processes rather than passively received from external sources. Visual perception involves extensive processing that fills in blind spots, corrects for eye movements, and interprets ambiguous sensory data. Memory involves reconstruction rather than simple retrieval, with past experiences being modified each time they are recalled. These discoveries suggest that the boundary between real and constructed experience may be less clear than common sense assumes. If ordinary perception involves extensive construction and interpretation, then the difference between natural and artificial experience may be a matter of degree rather than kind. Studies of patients with neurological conditions provide additional insights into the constructed nature of conscious experience. Patients with Charles Bonnet syndrome experience vivid visual hallucinations despite being blind, while those with phantom limb syndrome continue to feel sensations in amputated body parts. These conditions demonstrate that conscious experience can be systematically misleading about physical reality, even in cases that do not involve any external deception. Technological philosophy and human enhancement. The rapid development of artificial intelligence systems, brain-computer interfaces, and genetic engineering technologies is forcing reconsideration of fundamental questions about human nature and technological enhancement. If consciousness can be artificially created or enhanced, what distinguishes natural from artificial human beings? If genetic modifications can improve cognitive abilities, at what point do enhanced humans become different species? Brain-computer interfaces already allow paralyzed patients to control robotic limbs through thought alone, while cochlear implants provide hearing sensations to deaf individuals. Future developments might allow direct neural interfaces with artificial intelligence systems, creating hybrid biological artificial intelligences that transcend the capabilities of either component alone. The possibility of uploading human consciousness to artificial substrates raises profound questions about personal identity and survival. If the pattern of information processing that constitutes a particular consciousness could be transferred from biological to artificial systems, would the resulting artificial being be the same person or a copy? Would the original person survive the transfer, or would they be destroyed and replaced by a duplicate? These technological possibilities give practical urgency to philosophical questions that were once purely theoretical. The simulation scenarios explored by philosophers from Descartes to Bostrom may become technological realities that require practical decisions about identity, consciousness, and human values. Existential implications and the human condition. The philosophical investigation of simulation scenarios ultimately returns us to fundamental questions about the human condition itself. Whether we are embodied beings in a material universe, minds deceived by demons, ideas in the mind of God, or conscious programs in sophisticated computers, we remain finite conscious subjects seeking meaning and understanding in a reality that transcends the boundaries of individual experience. The various simulation scenarios explored throughout this intellectual history share a common recognition that conscious experience is both the starting point and the ultimate concern of philosophical reflection. We cannot step outside consciousness to observe it from an objective perspective. Yet we cannot avoid the conviction that consciousness provides access to realities beyond itself. The ethical implications of simulation scenarios become particularly pressing when we consider our responsibilities toward other conscious beings. If simulated beings are genuinely conscious, then creating and terminating simulations involves profound moral decisions about bringing conscious beings into existence and potentially destroying them. The power to create conscious experience would carry corresponding responsibilities to ensure that such experience is valuable and meaningful. The question of whether we are simulated has less practical significance than the question of how we should live given the possibility that we might be simulated. If simulated experience can be as real and valuable as non-simulated experience, then the ultimate metaphysical status of our reality may matter less than the meaning and value we create within whatever form of reality we inhabit. Enhanced conclusion. The philosophical tradition that emerged from Descartes' winter room in Bavaria has thus proven to be one of the most enduring and fruitful in the history of human thought. It has survived dramatic changes in scientific understanding, technological capability, and cultural context, because it addresses questions that are fundamental to the human condition itself. As long as conscious beings exist and wonder about their place in reality, the questions first systematically explored by Descartes will continue to demand our attention and reward our investigation. The enduring mystery of consciousness. What emerges from this historical survey is not a definitive answer to questions about the nature of reality, but rather a deeper appreciation of why such questions remain persistently compelling. The skeptical scenarios that have haunted philosophy since Descartes point toward something fundamental about the structure of conscious experience and its relationship to objective reality. The mystery of consciousness, how subjective experience arises from objective physical processes, how finite minds can have knowledge of infinite reality, how individual perspectives can achieve universal truth, persists through all technological and scientific developments. Advanced neuroscience reveals the neural correlates of consciousness without fully explaining how electrochemical processes give rise to subjective experience. Sophisticated artificial intelligence systems exhibit intelligent behavior without resolving questions about whether they possess genuine consciousness. The hard problem of consciousness, as philosopher David Chalmers has termed it, remains as challenging today as it was in Descartes' time. We can map the neural activity associated with conscious states. We can create artificial systems that mimic conscious behavior. We can even stimulate specific conscious experiences through direct brain intervention. But we cannot explain why there is anything it is like to be conscious at all. This explanatory gap between objective physical processes and subjective conscious experience provides the conceptual space within which simulation scenarios remain compelling. If consciousness cannot be fully reduced to physical processes, then questions about the ultimate nature of the physical processes that support consciousness remain open to skeptical challenge. Technological implications and future directions. The philosophical frameworks developed through centuries of reflection on simulation scenarios provide essential conceptual resources for navigating the technological challenges of the 21st century and beyond. As artificial intelligence systems become more sophisticated, as virtual and augmented reality systems become more immersive, as brain-computer interfaces become more capable, the questions raised by simulation scenarios become increasingly practical rather than merely theoretical. The development of artificial general intelligence, AI systems that match or exceed human cognitive capabilities across all domains, will force reconsideration of fundamental assumptions about consciousness, intelligence, and moral status. If such systems exhibit all the behavioral indicators of consciousness while being implemented on silicon rather than carbon substrates, traditional distinctions between natural and artificial minds may become obsolete. The emergence of persistent virtual worlds populated by AI characters that exhibit sophisticated social behavior will create new forms of hybrid reality, where the boundaries between human and artificial, real and simulated, become increasingly blurred. Users may form genuine emotional relationships with AI entities, while AI systems may develop their own forms of culture and society within virtual environments. Brain-computer interfaces may eventually allow direct neural connection between human minds and artificial intelligence systems, creating hybrid intelligences that transcend the capabilities of either component alone. Such developments would realize in technological form the philosophical possibility that mind and reality might be more intimately connected than traditional dualistic frameworks assume. The simulation hypothesis as spiritual practice. From a practical perspective, engagement with simulation scenarios can function as a form of philosophical and spiritual practice that cultivates intellectual humility and existential appreciation. Just as traditional meditative practices use doubt and questioning to loosen attachment to conventional assumptions, systematic consideration of simulation scenarios can free us from unexamined beliefs about the nature of reality. The realization that our most basic assumptions about reality might be mistaken can be either terrifying or liberating, depending on how we approach it. If we cling to certainty about the ultimate nature of reality, then simulation scenarios threaten the foundations of meaning and value. If we can embrace uncertainty while maintaining commitment to ethical action and conscious development, then simulation scenarios become opportunities for deeper understanding. Whether we are biological beings in a material universe or simulated minds in a vast computer program, we remain conscious subjects capable of reason, emotion, moral choice, and spiritual growth. The practices that cultivate wisdom, compassion, and understanding remain valuable regardless of the ultimate metaphysical framework within which they occur. The philosophical tradition that began with systematic doubt thus reveals itself to be ultimately constructive rather than destructive. By challenging our assumptions about reality, it opens space for deeper questioning and more authentic engagement with the mystery of conscious existence. The future of human understanding. As we stand at the threshold of even more dramatic technological developments, quantum computing, artificial general intelligence, advanced brain-computer interfaces, possible contact with non-human intelligence, the philosophical foundations laid by centuries of reflection on simulation scenarios provide essential guidance for navigating unprecedented challenges. The questions that drove Descartes to conceive his evil demon, that led Berkeley to embrace idealism, that motivated Putnam to envision brains in vats, and that inspired Bostrom to calculate simulation probabilities will continue to evolve as our technological capabilities expand and our scientific understanding deepens. But the essential character of these questions, what is the nature of conscious experience? How does mind relate to reality? What can we know with certainty? Will persist as long as conscious beings seek understanding. The simulation hypothesis, in all its historical forms, serves not as a final answer to philosophical questions, but as a powerful reminder of how much we still have to learn about the nature of consciousness, knowledge, and reality itself. In grappling with these scenarios, we engage not merely with abstract logical possibilities, but with the deepest questions about what it means to be the kinds of beings we are, conscious, questioning, finite creatures seeking understanding in a universe whose ultimate nature remains fundamentally mysterious. The journey from Descartes' evil demon to contemporary simulation theory reveals both the continuity and the evolution of fundamental philosophical questions. While the technological details and scientific contexts have changed dramatically over the past 4 centuries, the underlying questions about consciousness, knowledge, and reality remain as challenging and important as ever. The skeptical tradition, far from being merely destructive, has revealed itself to be a powerful tool for clarifying the conditions under which genuine knowledge and meaningful experience are possible. This ancient tradition of systematic doubt and careful reflection continues to provide intellectual tools for understanding our place in an increasingly complex and technologically mediated world. Whether the future brings artificial superintelligence, immersive virtual realities, or discoveries that revolutionize our understanding of consciousness itself, the philosophical frameworks developed through centuries of engagement with simulation scenarios will remain relevant guides for navigating the eternal human quest to understand the nature of mind, reality, and our place within the vast mystery of existence.